Swayam Prabha. Digital India. Educated India.
My name is Lokesh, and I'm a part of a research group here called C9. It's a part of the systems engineering group and chemical engineering. So today I'm going to talk about unsupervised learning. But before we get started, I think see how many people have heard of things like information theory before? Just a show of hands. No information theory, but I would say, but it permeates everything. All your phones run on it. So I would say all the algorithms that run on it are backed by information theory. Okay. So okay, let's get started. So a few things about C9. C9 is a group basically that's headed by Professor Raghunathan Rangaswamy at IIT Madras. And so as a part of it, we are about 40 students who actually kind of discuss various ideas, and we have regular talks and also work on a lot of research problems. So as a part of it, what you will see in the next 3 days will be a series of talks from this group. So today will be me from 9 to 11. I talk on unsupervised learning, and tomorrow it will be Shubham. Shubham will talk about a topological data analysis, and the third day on Wednesday you will have Ilan and Rohini talk to you about group theory. So, have you heard of these terms like topology or group theory? Anybody? Group theory, yes. Okay. But I think, but the way I think this should go is basically at any point of time you don't understand, yes, you can just stop and ask. But at the end of the day, if you go with a high level overview, that is okay. The details are not so important at this point. Okay. So, generally, what do you understand by learning actually? What comes to your mind when you say learning? Answers? Yeah, in some sense you update, you get some new information and then you get, yeah, go on. Yeah, at the end of the day, it's more about you get some information, you update whatever you have, your beliefs and your knowledge base, and then you have actually learned something new about maybe it's as mundane as things around you every day, but then you get a new perspective, you get a new, I would say, way to look at the same things, or sometimes totally new information also comes. So in this particular case, I'm going to talk about something called unsupervised learning. And I would say there are a lot of other kinds of learning, something called supervised learning or self-supervised learning or reinforcement learning. And all this jargon you will hear, I would say, left, right, center, across, I would say, all the machine learning and AI literature. I think basically almost like anything that has to do with, I would say, all your AI algorithms, all your facial recognition algorithms, for example, I would say anything that you're using on your phones, apps, everything. A lot of them actually are powered by AI and ML that actually, I would say, has some kind of a learning embedded in it. So I'm going to talk about unsupervised in the sense when you actually kind of look at reinforcement learning. What tends to happen is, let's say you're riding a bicycle. Let's say you kind of make a mistake and fall down. So what happens is if you do it the wrong way, you're going to get a penalty. You fall, you get hurt. But then if you do it right, somebody is going to tap on your shoulder and say, hey, this is you're doing really well. So that reinforces basically as you do it again and again, and I would say you kind of learn some policy, what's the right way to do this, or what's the wrong way to do this. So unsupervised learning in some sense doesn't have any of this reward system. You have some data and you have to make sense out of this data. So how do you do that? So that's what we'll talk about. Nobody's going to give you any rewards for this. Just you have some random splatter of data, and how do you make sense out of it? And the point I'm trying to make is all of you are doing it all the time. From the time you're born, you actually are faced with a lot of data and you make sense out of the visuals that come. nobody teaches you grammar. You actually learn your mother tongue basically at home. Nobody teaches you the rules of grammar at age 1 or 2. You try to kind of, you're bombarded with so much audio information and you try to gradually learn the rules. So that is basically unsupervised because there's nothing like correct. You start begin to make, I would say, a sense of faces, or you start begin to make sense of the words. So that's more like, I would say, there's nothing like, I would say, reward or loss. Basically you learn from the data. So what I will do in this talk is I will actually kind of give you guys a bit of motivation. I'll show you some experiments from neuroscience. Then what we'll do is we'll go to an example to see how we'll take a small sandbox example to make, I would say, sense out of basically random data. That's what we will do. The third thing we'll do is we'll see the implications of this all day. So let's get started. So the first experiment that I want to mention is about retinal prosthesis. So what happens is in some cases people lose sight because basically there's a problem with the retina, but the optic nerve is okay. Or sometimes they have a problem with the retina, they also have a problem with the optic nerve, but the visual cortex, your brain is okay. So now the question to ask is, how do you actually kind of, I would say, let's say, give him, I would say, as in second, I would say, stab at vision or something. So what people have done is, they actually take a electrode array. They take a electrode array and they implant it, and then whenever a photon bombards the receptor, basically it will fire. So, and then it will be a bundle of fibers that will actually get embedded either into the signals going to the optic nerve or directly to the visual cortex. So here what's happening here is, let me see, okay, this one is, so here is the array. And then what will happen is basically this is the array that's actually putting all the signals into your optic nerve here. But then very well what you can do is this, you can actually take this array of signals and directly put into the visual cortex, directly into the brain. You can bypass the optic nerve if the optic nerve is damaged. So, but as you all know, basically this one, the electrical signals are, I would say, are very different from the biological signals that as in your retina would actually send to the optic nerve. But then what happens is basically if you ask, though the signals are very different, what happens to the person who is actually implanted with this device? What do you think happens? Louder, yes.
Brain learns how to process the new information that is given.
Yeah, so basically the question is how. So because it doesn't know the code for the new information. The way new information is encoded is different, right? So how does it do this? That's the main question that we'll try to answer today. So this is experiment 1. Experiment 2. As in generally in the brain, what happens is the vision is supposed to be, as in it's actually, people know that it's processed in the visual cortex. If you actually look at audio, all the audio information is processed in the auditory cortex. Similarly, for example, touch, that's somatosensory cortex, and motor cortex that actually deals with movements. So every part of the brain specializes in a specific kind of, I would say, processing information. But the question to ask is there something so sacrosanct about that part of the brain processing that specific information or not? That's what we want to answer. And what do you think it is? What do you think it is? Let us say basically I try to kind of, let's say, I take the visual information and I don't send it to the visual cortex. I reroute it and send to the auditory cortex. What happens? What will happen? That means, can you see? How? How? That's the question. The point is basically yes. So, yeah, go on. Okay. Any more guesses?
People have a peculiar condition like wherein they can see sounds and hear colors, something like that will happen.
So that's synesthesia. But here, what happens is they actually did this experiment and in MIT, and what they did was they took a ferret and a very young ferret, and they took all the optical nerve, and actually here you can see that how they rerouted the information. So in this particular image is the normal cortex. What happens is, this is the eye, and this goes to LGN and then to visual cortex and superior colliculus. Here is the auditory wiring. Basically from here it goes into MGN and then to auditory cortex. So in the experiment that they did, what they did was they actually tried to kind of cut off the I would say the pathway to the superior colliculus and then connected it, rerouted MGN this way, and then this information goes to this thing. So there is experiment, and then they let this ferret go into the natural world, and then basically it's getting natural stimuli, and to the surprise, this did not exhibit any kind of abnormality. It worked like normal ferret. So this is the first time basically people have proved for the experimentally that your brain can adapt and rewire itself. So basically now what you see, as in, so all the visuals here I would say are evidence for as in what's happening. So what you should take away from the slide is basically in the early stage of development, when you actually kind of send some stimuli to a part of the brain will try to rewire itself in an attempt to interpret that input. Just the way basically we saw the previous case where basically visual cortex, basically you actually kind of send the information directly, a different kind of information, but it tried to adapt. But in the early stages it does extremely well. At the later stages it's difficult because the wiring becomes, I would say in some sense basically it's difficult to rewire, but it's possible. Any questions? Are you guys clear what's happening here? Experiment?
Was this performed in humans?
Sorry?
Was this performed in humans?
No. This is with ferrets actually. I don't think it's. I think it will be very difficult. I think you get a lot of clearances to do this on humans. Something goes wrong. But this is actually on rats. But for humans, I'll give you an example. What tends to happen is, have you seen any patient who had paralytic stroke? So what tends to happen in patients with paralytic stroke is they lose function, sometimes almost like one whole side first. Yeah, so they cannot, I would say, move any part here. I would say that they cannot move the hand. So what tends to happen is in those kind of patients, there is some kind of a block in the brain that kind of, I would say, stops, I would say, the function, and basically the whole area of the brain basically that actually governs the function of this side. If it's on the left side, it's the right brain. That actually some of the brain cells are dead, some of the areas are dead. So now what you do is basically, let's say you put them into some rehabilitation, some clinics. About 15 days, 20 days later, you see that they are able to resume function. Like they start, I would say, gradually moving their hands, and they start moving as in kind of sensing what's happening here and things like that. So the question to ask is, what happened? During the rehabilitation, did that part of the brain come back to life, or basically the dead cells, did they come back or something? Has it resumed the function? And the answer is no. Once it's gone, it's gone. It cannot resume. So what happened was basically the other parts of the brain that were doing other function have taken over this function of this part. So the other parts, basically the other parts of the brain that were doing other function, that function slightly weakens. But then you regain your ability to function on this side also. So in humans, you can actually see this as an example. Does that answer the question? Okay. Yeah.
How exactly does rewiring actually take place?
So basically I would say nobody knows at this point. That is the reason why I would say I'm presenting this motivation. So I'll tell you basically some experiment. For example, we have a proposal of how I would say how it works. As in some networks it works for us. I'll show you at the end. But that there is no way to say that is how the brain does it. It's one way to do it that we think, but that might be, but might not be. We'll come to that to then. But that's an open problem. So what I'm presenting to you are actually problems that actually, I would say I'm just presenting experiments, but a lot of, I would say, theory and things like that is still unsettled. It's not, people don't know actually. Can we move to the next experiment? Yeah, go on.
So how long does it take the brain to rewire itself?
Actually, the scales are almost dynamic in some sense. Sometimes basically it happens in a matter of minutes, depending on the task. For example, given the visual input, people have tried this. You'll try to close one eye and just give stimulus to one eye and see how it rewires. And then basically, so this part of the stimulus tries to take over that part of the brain that used to process stimulus from this eye. But then you open this eye, and then this will kind of basically go ahead and, I would say, reconquer that area in some sense. So this is happening almost dynamically in real time. But depending on the tasks and this depending on basically how easily the brain can adapt, as in depending, for example, if it's early stages of development, it is really fast. Later stages of development, I would say it is a bit slow. But essentially to answer your question, it happens in real time. Yeah. Questions? Okay. We'll move to the next experiment. Okay. So what I'll show you is a bit, I would say, let me kind of tell you what this experiment is. So this experiment is from a EPFL. What they do is basically as a part of Blue Brain project, which is actually has been running for 20 years now. They want to take a mouse and then kind of try to, I would say, see how the brain of the mice is wired, the connectome and things like that. So, and then this is one specific experiment from one specific project from that particular experiment. So I'll just try to explain to you what has been observed. So have you ever seen a neural network before? Like, have you seen how the neural network looks like? So more like you have some nodes like inputs here, and then you have some hidden layers, and these things send information, and then let's say you have one output, let's say gross. So have you seen this kind of structures before? Yeah. So here are inputs, here are outputs, and here is the hidden layer. And now what tends to happen is you look at this architecture, and I'll define an architecture called simplicial architecture. With simplicial architecture, have you heard of something called a simplex? No. Okay. So let's say you have, I would say, n nodes. When all the nodes are connected to all other nodes, then it's called a simplex. If I have 2 nodes, both are connected. If I have 3 nodes, what you get is a triangle. And if you have 4 nodes, you get a tetrahedron. Is that clear? That's all. Okay. So now what happens is, as in you can say this is a simplex of order 2, order 1, order 3, so on and so forth. You can say. Now what we want to say is basically here when they actually did these experiments and they actually saw when the information is propagating in the network, they actually measure to see how the information is propagating. What they see here is basically you actually see here there's a simplicial structure here, which is actually, I would say, this is like from the tissue, but actually the connectivity pattern is like this. And so the simplicial dimension for this are almost like 6 and 7 here. So what that means is basically here you don't have any simplex beyond lines that basically of dimension 1, but then you actually have simplices that are of higher dimension like 6 and 7 here. And that's the most important point to note here. And why is that important? The reason why that's important is because what that says is the way our networks process information, all your networks basically, all the AI ML algorithms basically perform operations on this network. But then if you were to actually look at the way brain performs, this is not the kind of architecture that the brain uses. It uses a very different architecture, and it uses this kind of architecture. So now what is the evidence for this? So what they did was they took a brain tissue, and then what they looked at is basically they looked at the connectivity patterns, and they saw how the simplicial count is. Let's say, for example, how many 2 simplices are there, how many 3 simplices are, so on and so forth. And then what they did was, this is for a network that is from the brain versus you actually can generate a random network. If you have a random network, once again they did the same thing. Look at the distribution, and then what you see is basically if the brain is rewiring randomly, then what that means is you should see the network very similar to a random network. If the brain is using some rule to rewire, then you will see some patterns. And guess what? As in here, the bottom corner, left corner here, what you see here, I'll just pass this for you actually. So as in, I just want you to take a look at this green line and the blue line. The green line is basically the distribution for a random network. What that means is this can barely go beyond as in simplest dimension of 3 and greater actually. But then if you see the network from the brain, you see that the simplicial dimensions go beyond 5, sometimes even 7 and 8 here. So the kind of network architecture in the brain is very different from the network architectures that we deal with. And it's not surprising that actually we perform computations way more efficiently than any of the ANNs. For example, you just have your breakfast or something and lunch and you function for the whole day. You're doing image recognition, you're doing voice recognition, you're able to understand concepts, doing all of this stuff. And you don't need so much storage space. Like for example, data centers occupy a lot of space, a lot of energy. And so in some sense, basically, our architecture is very different from the way ANNs work. And then the biological architectures are definitely at this point very superior. So as in whatever you want to do tomorrow is basically, I would say, you want to improve the architecture of your, I would say, your neural network in such a way that it computes efficiently. We will get there. Questions? Yeah.
What is a simplified dimension?
So let us say, for example, you have 2 nodes. N is equal to 2. Then the simplicial dimension is 1 here. Let us say, for example, n is equal to 3. So for now, let's say basically n is equal to 4. So let us say, for example, if n is your number of nodes and let's say k is a simplicial dimension, k is equal to n minus 1. Just take it for now. So, but I would say, but the point I'm trying to make is these kind of structures actually do not show up in ANNs, but these kind of structures do show up in biological networks, and that has been established from this experiment. So I will not go into this one, but I would say we'll come back if you have time. Right. Okay. So questions? Any questions about this experiment? Okay. So what I want you to see is basically here are, I would say, splatter of points, and in both cases basically as in there'll be some kind of they're moving in 2 dimensions. But what I wanted to ask you is, do you guys see a cube anywhere? Yeah. So basically, do you see the cube in 3 dimensions? And can you actually kind of as an even point out the axis of rotation? You're able to do all of that stuff. Yeah. So the point is basically what happens in the second dimension, second movie actually. Do you see any kind of 3-dimensional, I would say, object there? 2 dimensions. So as in both of these pictures, in both of these movies, what you see is all the points are moving only in 2 dimensions. Clearly, all the points are moving in 2 dimensions, but your brain makes, I would say, perceives the 3rd dimension in the first picture, first movie. Do you agree with me? Now, how do you perceive this? How do you perceive this? From a 2-dimensional data, how is your brain projecting 3rd dimension? We don't know at this point. We don't know at this point. Let's move to 3rd. Okay. Now, there's another, I would say, point that I want to mention is here. On the left side, everybody agrees it's A, but all of them are A, but they are, I would say, with some variance. Some are changing in color, some are, I would say, rotated, some are scaled down, some are scaled up, but then your brain is able to say all of them are A. So basically, irrelevant of all these transformations, your brain is going back and is able to say what it's actually the object is. So the idea to identify object is basically to invert the transformation that you have done. That's already done. The transformations are done in the real world, but your brain inverts these transformations. Now the question is, how does it invert these transformations? And in the second one, you actually see an object that's rotated in 3 dimensions, but actually you're able to say, but both of them are the same. You probably take 1 or 2 seconds, but you're able to say. So you're actually rotating it in your, I would say, in your mind and saying basically, oh, if I rotate this by like maybe 90 degrees or 45 degrees, then both of them overlap, and hence basically this, I would say, the same object. There's some invariance. So all of this is being done, but then how do you actually replicate this in your computational networks? How do you make your machines do this? And which is still a hard problem actually. Now, I'll also mention basically, I would say there's something called log polar transformation. What happens? Yeah, sorry.
How does the brain decide that it needs to
So we don't really understand, at least I don't really understand, but what we know is basically a lot of these transformations are biological hardwiring. It has learned it evolutionarily, but how, we don't know. And that's the question that I'm posing today. I'll show you some. So basically, look at this, right? So what happens here is basically, let's say this is your field of vision and all these circles, and now you're actually focusing on some object in the center, let's say. And then so now what happens is, I actually use this particular transformation. At this point of time, don't worry about what the transformation is. But what I wanted to say is, if I use this transformation, which is also a conformal mapping, then what happens is, this, from this point, this black one gets mapped to this one, this black area gets mapped to this one, and then these three get mapped here, and these three get mapped, or these two get mapped here. Is that clear how it's going? Now, then as in, why is this transformation even important? As in, actually your brain does this. When you're actually seeing something, you're actually doing this. So what happens is, when you actually look at any scene, let's say you have some xy coordinate there, the way it projects is not exactly xy. What happens is, it transforms into this rho theta coordinates, and that is how it maps the image, that the scene that you're seeing, onto your brain in the coordinates. So basically, this is what the transformation is, and this is how it gets mapped. So why is it doing this transformation? There's some very interesting properties about the transformation. We'll just see in a minute. But actually, if you look at it, basically this one, actually the ones that are closer to the center are actually scaled higher here. And basically, I would say, and the ones away from the center are scaled a bit less. But at the same time, basically, you can actually see, let's look at this example. I take the same M. In one case, okay, it's upright. Other case, it's rotated. In the third case, it's actually scaled down, a smaller version of it. Now, let us say you take this image, and then you run through this transformation, and then you actually map it on this map. What you see is basically, this is what you see. And now you take this image, and then you do the same transformation, and then you see this image, and then the third one, so forth. But what I wanted to point out is, now just notice between the first image and the second image and the maps, this map is almost same, except that basically this is actually moved down, this got moved up a bit. So any rotation, you don't need to do rotation. Now a rotation operation becomes translation operation. That's what happens here. A translation in the vertical direction. A rotation here is a translation in the vertical direction, and a scaling operation, let's say from here to here, is actually a translation in the horizontal direction. Actually, this one and this one, there's a slight, I would say, movement here. If you actually scale further down, actually you'll see a bigger movement. So what's happening is, your brain is actually automatically, as in using some kind of a built-in function to be able to do such a mapping, which actually makes a lot of operations easy for you. So how is it doing that? And why is it doing this? How does it know it should do this operation? We don't know how it does it. But evolutionarily it has wired out. And how did the evolution of this network happen? That also we don't know at this point. Yeah. But as a matter of fact, this is actually how it is done. You know that experimentally these transformations happen in the brain. Questions? All set? Okay. So what I ran you through is a bunch of experiments. First experiment, where you actually saw some data, and how do you make sense out of this data, which has very different kind of a encoding scheme. And later on, basically, we saw how the brain rewires itself to be able to interpret the input that's coming in. In the third experiment, you saw that the way our networks are working versus basically the way brain networks are wired are very different. The topologies are very different. In the next few experiments, basically what you saw was basically more like, how does, I would say, brain perceive 3D objects from 2D images. And so I would say for a lot of these questions are still open, but what I will do now is basically try to answer at least the first question. As a part, what you'll do is basically I'll walk you through some kind of basics, and then we'll address the question of how do we interpret data. random data, basically as in seemingly random data, but let's say if there's some underlying structures, how do you get the structure out of it? And more like as in, so how does the brain do this? And it is not actually doing an algebraic transformation, but it's actually doing some topological transformation, because basically all the functions are represented by networks of neurons, and this topological connections, as in the topology of the network, determines what function as in it's able to represent, and none of this is known at this point. Let's move on. The first sandbox example. So what I will do is basically, how is it if you actually giving a seemingly random data without actually telling you how it's organized, what happens? So let's say as in this, I don't know if you can see, there's a lot of zeros and ones here, and this is how things are encoded on your chip, on your phones, on your hard disk, on your computer. Now we ask you to make sense out of this. What do? You tell me. How do you make sense out of this data? So this is what your brain is always faced. When you're born, basically it sees a lot of data. This is actually, for example, encoded like this, but basically you can always think about things like images. You see a lot of images, you don't know how to parse them. There's a lot of data that's coming there. Audio, people are talking 101 languages, and a lot of sounds are coming, natural sounds are coming, some sounds from animals, some speech is coming. Then how does your brain make sense out of all of this? Right? For example, that's why we actually look at this particular example, because as in you want to start with something simple, and this is something that you already know. We are actually kind of just, I would say basically acting as if we don't know, but as in we know what the structure of this data is. But I'm asking, when you actually, I'm showing this data to you and asking, how do you interpret this data? How do you go about it? Go on.
You translate it from binary to an understanding.
That's right, but as in you didn't know it was binary encoded, no, in the first place. It's just random data. Okay, you can see the symbols and say, okay, it's 0, 1, it's binary. But how do you bring it back, let's say? What is the structure underlying this data? That's the question we'll answer. This is a sandbox example we will look at, I would say, in the next, I would say, 1.5 hours. Using this, we'll try to understand how actually the brain encodes information. Okay, so actually, let's kind of cheat a bit actually, and then see what happens. So, if you look at it, basically, as I said, there's this binary data. Out of this binary data, basically, as in this binary data are representing a lot of characters and digits. Let us say you're looking at textual data. Let's say a novel is encoded in that format, and I give you the data, just zeros and ones. And now what happens is basically, as in underlying all the zeros and ones is some binary, I would say, binary, all the binary data is basically some characters and digits. And underlying all these character and digits, basically there's some words basically that people are using to express some idea, as in some specific objects and things like that. And over it you have sentences, and which is expressing a specific idea. So this is how this is all the structure that's in that data. And now what I'm asking is basically there's a novel or something that's binary encoded, and that's given to you in binary format, or some alien which doesn't know anything about English or something. Then how does it actually, what can it make out of it? And the answer is basically it can make out of everything, all the knowledge basically that you already know. How does it do it? It does statistically. It's looking at structures underlying this data. So before that, what I would like to do is basically kind of just quickly run through some ideas in, let's say, entropy and information. So, have you guys heard of entropy, information, entropy? So, in what context did you hear entropy? Huh? Sir? Sir?
It's a measure of disorder and chaos.
And what about you? Where did you hear about entropy? Thermodynamics. Okay, yeah. Most like basically it's like irreversibility and things like that. Okay. So we'll actually as in there's a connection between thermodynamic entropy and information theoretic entropy, which we'll not go into now. What I will talk to you about is information theoretic entropy. So what we'll talk about is basically, let us say, as in what do you understand by information? What do you understand by information? So let's say what is more informative, what is less informative. So let's say if an event has already, let's say you already know a lot of, I would say data about some event, then any new data that's going to come in, it's not going to give any new information. It gives you so basically that particular, I would say, data has very less informational value for you. But whereas if you actually know very little about something and the data comes in, it gives you a lot of information value. Do you agree on this? So now what happens is, let us talk basically, let's say the probability of the event, let's say. The probability of the event, let's say occurring is 1. This you already know. You already know that let's say somebody tells you that KKR is going to win. Then there's, I would say in some sense, there's, you have complete information of what's going to happen. You seeing the match doesn't give you, I would say, information about the outcome, right? So then I would say the informational value here is close to 0. You agree? Now let's say basically the probability of the event occurring is close to 0. Let's say some epsilon. Then what happens is, because the probability is so small, let's say basically somebody tells that, I don't know, SRH is going to win. And then what happens is, and you say like basically they've been winning all matches, let's say, and the probability of SRH is winning very high. But then upset comes and surprise comes, and then SRH loses or something. Then what happens is, the information what you get from that, I would say, the event is very high. So here it's very high. So you want some function that actually can model this. And the function, basically the functional form that you want to look at is basically something that maximizes surprise in some sense. And log 1 by px is one such function. And people claim it's the only function. Now you put p is equal to 1, you get 0, and p is equal to epsilon close, it's very small numbers. Basically this becomes very high, and this will be very high. So this is about this particular event. For this particular event, this is the informational value you get. If the probability is p, this is the information content in that particular event. But let's say, for example, if there are a lot of events and you want to kind of get the information value in all, for example, let's say all these events, then what you look at is basically, and you have a distribution over all these events, probability distribution of all these events. And then you say, for example, if this is the information content in specific event, and the probability of it occurring is p of x, then I would say the average, the information is basically, I would say, you say p of x log 1 by p of x. Summation over x. Is this clear? So in some sense, do you agree that this is the amount of information content that all the events can give you? Are you with me? Are you lost? So this is nothing but entropy. This is entropy. This is the definition of entropy in information theory. So you can write H you can use any base. For now, let's use base 2. It's just easy. Let's say log base 2. And then this is what permeates almost all of information theory, I would say. And there's a lot of nice theorems by Shannon. Yeah. So what I'm saying is, let us say I have an event, and let's say the probability of it occurring is almost certain. I know that it's going to occur. Then what happens is, any new data that comes doesn't tell me any new thing about it. So the informational value in it is 0. Let's say the probability of event occurring is almost 0. And then the event actually occurs. Then it tells me something that I really don't know. I was actually underestimating, something happened. So then what happens is, the information content is very high. So I need some function that can mathematically model this. And I'm asking, what is the function that mathematically model this? So I didn't tell you how, but I just basically, I pulled it out of my head and said, if I want something like this, and then you come here. So most of the times what you do is, I would say, let's say, some cases you actually look at some phenomena and you see that when this happens, this should happen, and these are the constraints which should satisfy. So what you do is, you actually write them as axioms. Once you have these axioms, then you ask, what is the function that satisfies all these axioms? So I think our thing is, I would say, in a crude way, it's something like that. What we did was, we said these are the properties of my function that is actually quantifying information. When I said information, I said somebody tells me something, and I updated something and I have new information. I got something new, right? So now we wanted to in some sense mathematically model that, and that I would say our intuition, or basically our explanation of, I would say, the normal English explanation of information translates to this mathematical form I just said. For this particular event, I said there's a lot of events, and then for example, out of this lot of events, basically I want to quantify the information content in all these events, let's say. And then I'm saying that the events are basically, let's say, I is equal to 1 to n, let's say there's n events, and the probability of each event occurring is pi, is minus is coming here. So basically this is the informational value in that event, and the probability at which it occurs is basically into it is the information content that particular event gives me. And because there are so many events, basically it's a summation over all those events. Okay, are you with me? Yeah.
So why does this informational function be related to entropy?
How is the information power function relating to entropy? As a good question, but I don't know how to answer, but let me try. So in some sense, I would say entropy is also a measure of uncertainty. So when you have new information coming, your entropy goes down. What do I mean by that? Let's say, okay, let me tell you this. Let's look at this. Let's look at, I would say, let's take this example. Let us say this is, I would say, some string of length 3, and let's even consider even simple thing. It's a binary string. You with me? And now what I'm asking is, I'm asking you to guess what the string is, and if you get it right, I'll give you $1 million. Okay. Now, so basically, as in, what will be a guess? So what is the total number of guesses? I would say, let's say basically how many things that this can take? 8. It can take 8 possible things, because basically this can take 2 values, this can take 2, this can take 2, so it's 2 cube, and that becomes 8. So the total number of guesses you can take is 8, right? So there's uncertainty. So basically now, if I actually quantify the entropy of this, let's use this formula. Okay. And actually, if you look at event is basically some value which take 111,000. What is the probability of an event occurring? Any one of those events occurring? 1 by 8. Yes. So all of them are equally probable. So what will happen is, this is 1 by 8, and now this is also 1 by 8, and now the summation is 1 to n is 8 here, because they're total 8. Now what does this come to? This turns out basically you sum it, and then basically what happens is, because there's no, I would say all of them are same, it gets multiplied by 8. And you have log 8 base 2, because it's base 2, you can write this as 2 power 3, this is 3. So right now the entropy is 3. Do you see that? Now let me do one thing. Okay, now basically what happens is, as in, if you guess it right, you'll get $1 million. But what's the probability of you guessing it right? It is 1 by 8, because you guess one of them, and basically I would say 7 of them you're not able to guess. So the probability of you doing a random guess and getting right is 1 by 8. Now let's say, for example, I tell you, hey, the first bit is 1. I tell you this. Now what happens? The first bit is 1. What is the entropy of this? Huh? Sorry. The entropy, how is it 4? Let's work this out. The total number of possibilities you have is 2 into 2, 4, agreed? The total number of possibilities is 2 square, that's 4. Then, now we say basically the probability of an event occurring, all of them are equally probable, is 1 by 4. Then we'll actually go through the same thing, and then you say h is minus I is equal to 1 to 4, 1 by 4, log 2, log base 2, 1 by 4. Okay, is this clear so far? Now you sum and basically this 4 goes off because it is log base 2, 1 by 4, and then this becomes log base 2, this is 2 squared. The minus sign goes in and then it gives you a 2. So here for this case, we have, let's call this initial thing and entropy, and let's call basically I would say the next ij. Let's use j, second step. So the entropy went down. Did you see this? Do you see this? So how did this entropy go down? The entropy went down because you got a new piece of information. The information is this bit. So that is the connection between, I would say, entropy and information. So new information, I would say basically, reduces the uncertainty and it brings the entropy of the system down. It brings the uncertainty of the system down. That is the interpretation in information theory. It will be slightly different in thermodynamics, but there are connections. So now what happens is, let us say I give another piece of information. I say like, now what's the probability of you winning $1 million? 1/4. I give another one. Let's say I give you that this is also 1. Now what happens? What's the entropy? Yeah, entropy is 1. Ijk is 1. Entropy went to 1. And now what's the probability of you winning? 1 by 2. Yeah. So now what happens is initially your probability of winning is 1 by 8. Later it become 1 by 4. Now it become 1 by 4. So basically as new information came, the uncertainty has reduced and you know basically you're getting more and more certain about things. Do you see what's happening here? You get the point? Or basically I would say if I give this information, then I say I give a third bit, then there's nothing for you to guess. It's perfect certainty, as in you know what is going to happen, you know what is the winning number. So with every new information what's coming, what happens is basically the entropy is going down, and then with that basically uncertainty also goes down. When entropy goes to 0, let's say I give you all of these bits, and entropy is 0. Do you see that? The entropy is 0, it's perfect certainty. You know what exactly is going to happen. So in systems where the entropy is 0, you know the state of the system. So I would say in thermodynamics, I think what would have learned basically, you would have actually learned some, I would say something like a macro state and a micro state, right? So macro state are some variables that you see at a higher level like temperature or something, and then or some energy or something. So you have this macro state, but then you say basically what is the number of micro states it can take, and then you look at basically I would say I think something like minus kb summation of prop pi ln pi or something. So when you actually do all of that stuff, what happens is I think you get something like kb, I think log of w. This w is the total number of states, micro states for that particular macro states. Does it ring the bells? So as in this formula is very similar. For example, here it's n, the total number of states, but without the Boltzmann constant. But there are connections. So basically, if you guys are interested in the connections, I would suggest you look at something called Maxwell's demon. Have you heard about this Maxwell's demon before? So, so what's the connection between thermodynamic entropy and this? Who told you Maxwell's demon? Is it Balakrishnan? Okay. So anyway, Maxwell's demon. What do you see the connection? What's happening? As in, can you make a connection? How Maxwell's demon and this are connected? So what happens in the Maxwell's demon? What's the demon doing? Yeah, it feels like it's decreasing entropy, right? So does it violate the law of thermodynamics? It needs information. The thing is basically the very point that it has to let that one, I would say, let's say there's one atom that's coming in. Height, let's look at let's revisit Maxwell's demon. Can this go up? Okay, it doesn't go up. Okay, let's go. So in Maxwell's demon, what you have is basically you have some demon sitting here, and then there's some kind of a door here. Okay, let's do this a bit better. Okay, and then you have some kind of a, let's say you have something like this. This is a hot molecule, and let's say this is a cold molecule. Let's say now you have some cold molecules and some hot molecules and some more hot molecules here, and then you have some cold molecules here. And now what you do is basically this demon, whenever let's kind of designate this as the cold chamber, and let's designate this as hot chamber. Whenever a hot molecule is coming this way, it opens the door or gate, and the hot molecules goes that way. And whenever a cold molecule wants to go this way, it will not open the door, right? This is what happens, and vice versa on the other side. Okay. But now what happens is basically for it to open the gate when a hot molecule comes, what it should know is basically it should know, I would say this is actually, it has to keep track of the position of this. It has to keep track of basically that it's going to come here, and then that time it has to open a door, and it has to do this for a lot of molecules that are coming from either sides. And so what happens is the amount of entropy it generates in the process is so high that the entropy it decreases in the system is low. Are you with me? So it doesn't violate, I would say, the principles of thermodynamics. That's one argument. But I would say basically there's a lot of debate on this, but you can always look at it. But the question is basically what is the connection between information theoretic entropy and thermodynamic entropy? I think this one is I think it is a Pandora's box. You can have how much of a discussion you want. It's still unsettled. It's been there for a long time actually. Okay. Okay, now I think, but why are we talking about entropy? The reason why we are talking entropy is because basically we are actually talking about, I would say, its connection with information. How a new information, that's incoming new information, reduces the entropy of the system. Are you with me with that? Okay, now let's go. Now what I want you to do is basically, I think we have to stop at 50 or something, and then you take a break for 10 minutes and come back. Is that how it works? Okay, then I'd say, so this is the problem that we're going to solve. We use the ideas of entropy and things like that to actually kind of take a stab at this problem, and we'll solve this problem by the time we go out of the room tomorrow, by 11 o'clock today. So what I would like to see by the time you come out of the break is how will you solve this problem? Okay, yeah. Then let's take a break and we meet in 10 minutes. Okay, yeah. Thank you.